Myself, Dr. Keshavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss about laser glass spectroscopy. In this laser glass spectroscopy, last previous session we discussed on objectives and scope of research. That is the main topics covered under spectroscopy and its importance, electromagnetic spectrum, next motivation of lanthanide and rare earth ions, definition of glass, importance of glasses, finally basic properties of glass and advantage of glass. These topics are discussed in the last session. Today we are going to discuss about the outline of the today talk is on the thermodynamic and structural properties of lanthanide doped glasses. In this section we are going to discuss about the thermodynamics of glass formation, glass network formers and modifiers, structural features of glass and lanthanide doped glasses, variation of bond nature and variation of ligand anomaly. These topics today we are going to discuss about in the subtopic of the laser glass spectroscopy. So first initially we are going to discuss about the thermodynamic and glass formation. This is the very important. Thermodynamics means thermal properties of the glass formation. How glass formation takes place by using the thermodynamic properties. There are two main types of pathways that a liquid may follow on cooling to the solid state. Either it may be crystallized at or below the melting temperature. Tm is the melting temperature. So generally glass formation takes place below the melting point. That is below the melting point. That is the melting temperature of the glass formation. Or it may be undercooled sufficiently for forming a glass without crystallization. There is a glass formation. There is a crystallization phase also there. That means so glass will be formed melting below the melting temperature. That is very important. So glass is generally obtained by cooling a liquid below its freezing point. That is below its freezing point. The classical explanation of the glass formation is that when a liquid is cooled, its fluidity, which is the reciprocal of viscosity, decreases at a certain temperature. So there is a fluidity and viscosity is mainly reciprocal, that means inversely proportional. The viscosity means that is liquid nature. Viscosity, highly viscosity means liquid nature. The fluidity, its fluidity, which is the reciprocal of the viscosity, decreases. And at a certain temperature, if once the temperature increases, that viscosity also decreases. That's once temperature increases, viscosity decreases. So temperature decreases, viscosity increases. That is the reciprocal of the nature. That is below the freezing point becomes nearly zero. That is the liquid becomes rigid. That means very perfectly bonded. The rigidity happens. The curve, however, shows a change of slope at a temperature called the glass transition temperature. So below the glass transition temperature, that is very important. The curve, however, so this curve we can show in the next slide. The curve, however, shows the change of slope at a temperature called glass transition temperature, TG. This is TG, glass transition temperature. Below this temperature range, the glass structure does not relax at a cooling rate used. Which cooling rate we are used at that time? The glass structure does not relax at a cooling rate. Whatever you use at that time, it cannot relax. That is at the cooling rate used. The expansion coefficient, this expansion coefficient for the glass state is usually about the same as that for the crystalline solid. So this is a very important glass transition temperature in the glass formation, glass transition temperature, crystalline temperature and glass melting temperature. These three parameters are very important. At the same time, glass transition temperature is the very important for the forming of the glasses. Next, coming to this diagram is the effect of temperature and the enthalpy or volume of the glass. This is the figure source. This below figure source represents the enthalpy, temperature characteristics of crystal, liquid and glass. When a liquid is cooled to form a solid, the resulting cooling curve shows distinct differences from those of the crystalline and amorphous solids. See here this curve, the x-axis temperature and y-axis enthalpy. What is meant by enthalpy? Enthalpy is the measurement of energy in a thermodynamic system. The quantity of enthalpy equals to the total content of heat of the system. equivalent to the system internal energy plus the product of volume and pressure. Generally, the total energy, that means the equivalent of enthalpy energy, total energy equal to H equal to, that is, you can do product of volume plus pressure, volume V and pressure. That is the total energy. You can, enthalpy symbol is H, that total content of the heat of the system is equivalent to the system of internal energy, that is H, that is energy plus the product of the this is, that is total energy E equal H plus internal energy plus product of internal energy plus the product of the volume and pressure, volume V and pressure. This is the enthalpy. That is, the enthalpy is the measurement of energy in a thermodynamic system. The quantity of enthalpy equals to the total content of heat of the system is equivalent to the system internal energy E, that is internal energy E plus the product of the volume and pressure. So this is the enthalpy. So this, by using this graph, you can say the what is the where it is the crystalline forms glass when it is forms. By using this diagram, that is temperature versus enthalpy diagram, you can say the how the glass formation takes place. So here x-axis temperature, y-axis taken enthalpy. See here first curve, it will be crystal nature, that means slowly cooling. So that is the, if you see the temperature versus enthalpy, enthalpy also low, temperature also cool, low. It starts from low temperature, temperature of low, it will go the formation. This is the formation of crystals. Next is, so you see the glass formation, slow cooling glasses and slow cooled glasses and fast cooled glasses. Here is the glass temperature, glass transition temperature range. This is glass transition. See here this curve and this slope. By using this slope only, we can say that this is the slow cooled glass or fast cooled glasses. So these are the takes place below the glass transition temperature. These are the here. Next here, super cooled liquid and a liquid. So super cooled liquid and liquid, in between there is a temperature, that is a melting temperature. So here this is the which glass host, what is the melting temperature of the glass, we can see by using the melting temperature. So this state will be, it will occur in between the super cooled liquid and liquid. So here glass transition temperature takes place in the slow cooled glass and fast cooled glass. Here this slope and this slope, by using this slope we can measure the glass temperature range where it is the glass transition temperature. So slow cool temperature and fast cool temperature. So by using this one, we can measure the what is the glass transition temperature and glass melting temperature. So here the glass transition temperature can be determined by differential thermal analysis, DT analysis, by using the DTA, otherwise DSC, differential scanning calorimetry. The both instruments we can use to determine the what is the glass transition temperature, what is the crystalline temperature, what is the glass melting temperature. These three parameters we can able to study by using of these two instruments. That is, first one is DTA, that means differential thermal analysis, and as well as same DSC. But DSC range will be up to 1000 degrees centigrade, but DTA we can go up to 1500 degrees centigrade also. So by using this one, these two instruments, we can say the where the glass transition temperature, where is the glass crystalline temperature, what is the glass melting temperature. We can, three parameters, so we can clearly know the by using of these two instruments, DTA or DSC. Next, coming to the glass network formers and modifiers. So glasses have been prepared using different types of materials. The ability of a substance to form a glass does not depend upon any particular physical or chemical properties. This is very important. This not depend on the particularly physical and chemical properties. It is now generally agreed that almost any substance, it cooled sufficiently fast, could be obtained in the glassy state, although in practice crystallization intervenes in many substances. So here glass formers main is B2O3, boric oxide, SiO2, silicon dioxide, germanium, GeO2, germanium oxide, next P2O, phosphorus pentoxide. These are the very, very important glass formers. These are the very important glass formers, the borate glasses. If you use the B2O3 means we can prepare the borate glass. If you can use the SiO2, silicon dioxide, that means we can say the silicate glass former. If germanium oxide, if you use this, that glass former is germanium oxide. If you use the P2O5, Phosphorus pentaxide means phosphate classes. These are the important glass formers of the system, all of which come from a certain area of the periodic table, readily form glasses on their own when their melts are cooled and are commonly known as glass formers. So these are the glass formers: borate glasses, silicate glasses, germanium glasses, and phosphate glasses. By using this glass formers, we can prepare the different type of glass host materials. So these are the oxides of elements with intermediate electronegativity. These elements are sufficiently electropositive to form ionic structures such as magnesium oxide and sodium chloride, MgO and NaCl, sodium chloride, but also are not sufficiently electronegative to form the covalent bonded small molecular structures such as carbon dioxide. Instead, bonding is usually mixture of ionic and covalent, and structures are best regarded as three-dimensional polymeric structures. So generally structures are mainly best for the three-dimensional polymeric structures. So instead of this magnesium oxide NaCl, we need to bond. The bonding will be takes place at the time. It should be bonding is usually mixture of ionic and covalent and the structures. This is covalent nature and ionic nature should be taken place whenever the glass structure will be formed at that time. So these are the important glass formers and modifiers. So glass formers is mainly B2O3 and silicate SiO2 and germanium oxide GeO2 and phosphate glasses P2O5, phosphorus pentaxide. These are the very important glass formers. And the same we can use all these some modifiers is magnesium oxide, Na sodium chloride. These are the some additionally modifiers we can use to form the glass formers. Next, coming to there are some oxides like sodium oxide N2O, next lithium oxide Li2O, next potassium oxide K2O, next lead oxide PbO, and calcium oxide, which when added in a small quantity, that quantity is very important, that concentration, the moles percentages, we can use this modifiers concentration should be in the range of 10 to 15 mole percentage. So whenever you are adding the glass formers, the additional network modifiers we are adding, that is network modifiers as sodium oxide, lithium oxide, potassium oxide, lead oxide, and calcium oxide. Whenever adding to the glass formers, we have to use very less concentration, that is in the range of 10 to 15 mole percentage concentration we can use in the glass formers. To the glass network formers, oxides produce drastically change melting point and conductivity. Whenever adding these network modifiers into the glass formers, at that time it will produce drastical changes. In which parameter it will changes means melting point as well as conductivity and other parameters we can change the network system formers. So in the properties of the latter, such oxide also modifies the network structure of the glass and hence they are termed as network modifiers. So this we can call as a network modifiers. So by using this table, this is table shows the glass formers, modifiers and intermediates. So in this table shows the glass formers. What are the glass formers? First one, silicate glasses, SiO2. Next, germanium oxide, and that means germate glasses. Borate glasses, B2O3. Next, phosphate glasses, B2O5, phosphorus pentaxide. Next, tellurium oxide, the tellurate glasses, we can use tellurium oxide, TuO2. Next, arsenic trioxide, As2O3, arsenic trioxide, and also arsenic pentoxide, As2O3. These are the very, very important glass formers. Next, coming to the next second column, modifiers. So what kind of modifiers you can use? You can add into the glass formers is lithium oxide, first one. Second one is sodium oxide, Na2O. Next, potassium oxide, K2O. Next, calcium oxide, CaO. Next, barium oxide, BaO. These are the modifiers to add into the glass formers. These modifiers, we can add the that concentration mole percentage should be in the order of 10 to 15 mole percentage only. More percentage you can add in the glass formers. If you have the 100 mole percentage, you can add the modifiers in the range of 10 to 15. Remaining is glass formers. The other small quantities intermediates. So we can use third column is intermediates. The intermediates means glass formers and modifiers. There is you can add the other intermediate modifiers. That is the aluminum oxide, lead oxide, zinc oxide, cadmium oxide, titanium oxide, TiO2, titanium. These are the intermediate systems. So we can glass formers. Okay. See, only glass formers itself, you cannot form the glass system. We need to add modifiers or intermediates, then only glass will be formed. So glass former is very important, essential thing, but more concentration, if we take 100 mole percent, we can more than 60% we can use the glass formers. In addition to that, we can add the modifiers or intermediates. Without modifiers, anyway, we cannot form the glass formers. We cannot form, but we can add some modifiers. Then only you can form the glass system. So here you see the tellurium oxide and selenium oxide, the MOO3 molybdenum trioxide, that's WO3 tungsten trioxide, that's bismuth oxide, aluminum oxide, gallium oxide, and vanadium oxide will not form glasses on their own, but each will do so when melting with a suitable quantity of certain other non-glass former oxides. Hence, they are known as a conditional glass formers. That is called as the conditional glass formers. So, glass formers, we need to add some other oxides, that means non-glass forming oxides that we need to add. That is, we can add the vanadium oxide, aluminum oxide, gallium oxide, molybdenum oxide, selenium oxide, tellurium oxide, tungsten oxide, bismuth oxide. Again, these are known as a conditional glass formers. This is we can call as a conditional glass formers. So in this table, we can show the what kind of glass formers we can use, what kind of modifiers we can use, what kind of intermediates we can use to form the glass network systems. Next, coming to the structural features of the glass. So here, due to the absence of long range order, that means generally amorphous material or glass materials having the long range order. In case of crystallines, crystals having the long range order, but amorphous material short range order. But in this glass material, the absence of long range order, which is characteristic for the vitreous state, there is no single experimental technique which could produce a direct mapping of the glass network structures. Therefore, the elucidation of glass structures has become a major enterprise involving many different experimental and theoretical methods. There are many experimental and theoretical methods which yield different, often complementary information which can be combined to a structural model of a certain glass system. So these are the variable. So glass structural studies, we can use to study the glass structure. We need to know the diffraction and spectroscopy technique are the two kinds of analytical methods for studying the glass structure. We need to study the glass structure. We need to study the XRD, that means the short range order. Thereby, the structural information of glasses can be obtained by X-ray diffraction. XRD. By using X-ray diffraction, we use it to study the structural features of the glass. So, which glasses, if borate glass or silicate glass, telluride glasses, this is glasses, we cannot show any crystalline peak. We need to show this broad band, that is amorphous nature. Amorphous weightage means it is the absence of long range order, presence of short range order, very, very important. In glass material, amorphous weightage, it can produce the short range order. That means it cannot show any crystalline peaks, short or broad peaks we cannot get. Only this is the short range order we can identify in the glass network. This short range order we can identify by using the X-ray diffraction. That means by using the X-ray diffraction instrument, we can study the structural studies of the glass material, the amorphous materials. If you are absence of long range order, means that is called completely amorphous nature. You can say this is a glassy nature. So, presence of short range order. This short range order we need to find out by using the experimental study of by using XRT, that means X-ray diffraction. By using X-ray diffraction, we can study this is amorphous nature or crystalline nature. It is found the short range order means we can say directly it is amorphous or glassy nature. When you are getting long range order means crystalline peaks we can getting this, that you can say this is crystalline nature. So absence of long range order, we can say this is a crystalline nature. Amorphous nature. That is the glass system. Next, coming to the formation of glass. This is very important. According to the Churchson rule, that is the Churchson rule is for the formation of the glass. So the scientist is discuss about the 4 important rules for the formation of glass structure or glass system. That is, first one is an oxygen atom linked to not more than 2 glass forming cations. That is first rule. An oxygen atom linked to not more than 2 glass forming cations. So in any glass host material, we need to glass former cations. Is it not more than 2 glass forming cations? That is first rule. Second rule, the number of oxygen atoms around a cation of a glass forming cation must be small. It's very important. So the number of oxygen atoms around a cation of a glass forming cation must be small. That is second rule. Next, third rule. The oxygen polyhedral share corners but not edges or faces. So polyhedral means there are more than 3 or 4 faces. That means the oxygen having the corners. It share the corners of the polyhedral but does not follow the edges or faces. It only share the corners of the each and every oxygen atoms. That is third rule. Next, fourth one is if the network is to be three-dimensional nature, at least 3 corners in each polyhedral of anions with cations at the centers. This is the fourth rule. These 4 rules satisfies, then only we can formation of glass we can easily form. So whenever these 4 rules, this is discovered by the Richardson rule. The Richardson scientist is discovered, that is why he introduced the 4 important rules to form the glass nature. How glass nature will be formed. According to this rules only, glass will be formed. So glass structures. This violation of any one of these rules does not necessarily mean that the glass formation cannot occur, but it will be energetically less favorable. So this 4 rule must be important. At the same time, mean that glass formation cannot occur, but will be energetically less favorable. So if any 2 rules only satisfied means, but sometimes it will be possible, but energetically less favorable. So we can formation of glass formation is possible only very less probability only. So whenever the 4 rules will be satisfied, we can easily form the glass formation or glass systems. So according to these rules, glass network formers will be forming of the glass system. Next, coming to the term network former is now generally adopted for oxides capable of the glass formation. Oxygen ion which act as bridges between the structural units are called bridging oxygen. BO means bridging oxygens, called bridging oxygens. So whenever bridging the formers and the modifiers, there are bridging will be takes place. That is which act as a bridging between the structural units that called bridging oxygens. BO means bridging oxygens. In addition to the network formers, glasses may contain oxides which do not participate in the forming the network structure and which are called network modifiers. So here 2 things very important: glass formers, network formers. That is network formers nothing but a glass formers. The other one network modifiers. These both are too important. By using this, in between these glass formers and modifiers, there is a bridge is required to form the glass structure. So that is called bridging oxygen. So instead of oxygens, it will be go through the network formers. At that time, structure will be formation. So at that time, anion cation is interaction at the same place, the glass will be formed, produces. So this is the important networks, glass formers and network modifiers. In between, there is a bridging structure is a unit is required, that is called bridging oxygens, BO. So there are 3 principal actions of network modifiers in classes, which can be summarized for an A2O3 class as follows. A2O3 means that is formula of the glass formers. That is A2O3. That means breaking of AOO. That means metal oxide means AA is metals. A represents the metals. O means oxides. So bond and creation of non-bridging oxide. This A2O3, that kind of formula by using to breaking of network, that is non-bridging oxygen. By using, if you break any networks, you have to creation of non-bridging oxygens. The second one is increasing the oxygen coordination of cation A. Cations A. A is the cations, O is the oxides. Next, third one is a combination of both anions and cations. Both will use it to form. These are the 3 important principles of the network modifiers. By using network modifiers, these 3 important things should be happens. So by using this network formers and network modifiers used to, and there are the breaking of non-bridging oxygens. By using this all parameters considering, we can fabricate the glass system or glass network systems. Next, coming to the how the breaking of metal oxides will be leads to the creation of non-bridging oxygen. The creation of non-bridging oxygen is shown figure. So this is the creation of non-bridging oxygen. Yes, cation oxides AOO. Here that is oxides will be, that is we can say ligands. Ligands is nothing but a negative charge particle surrounded by the positive ions, cations, the positive ions plus metal oxide M2O used to 2 into these are the A, B, C. These are the creation of non-bridging oxygens. How non-bridging oxygen takes place? These oxygen ions carry a partially negative charge and are connected to the glass network at one end only. The resulting network gets loose, and by decreasing the connectivity, a larger flexibility of the structure is obtained. By using this creation of non-bridging oxygen, we can create the breaking of non-bridging oxygens. Next, coming to the lanthanide doped glasses. How this thermodynamic structures followed by lanthanide doped glasses. A technological important area in which recently there has been substantial interest is that of lanthanide doped optical glasses. Okay. Most of the glass lasers, laser glass spectroscopy, the most of the glass lasers have used lanthanides as the active ions. If you want to do the laser glass preparation, we need to add any lanthanide ions or aeronautical. That is the active ions act in the laser glass spectroscopy. So most of the glass lasers to date have used lanthanide ions as the active ions. Up to today, the lanthanide ions is the active ions in the laser glass spectroscopy. So because their electronic states of the unfilled 4f cell, the electronic configuration is each and every lanthanide rare ions, the 4 black elements. So 4f cell provide many energy level schemes suitable for laser action. That is why they are choosing the lanthanide ions or rare ions, because the electronic state of the unfilled 4f cell provide many energy level schemes. So each and every lanthanide ion having a different kind of energy levels. You see the samarium, dysprosium, prismodium or erbium, a different kind of rare elements or lanthanide ions. You will show the different kind of energy levels. So each and every rare element having the individual properties. So by using these properties, we can develop the laser glasses. That is suitable for the laser action. So racing has been obtained for all ions of series in glasses, in many cases involving several different kind of transitions. That is very much. So each and every lanthanide doped glasses having the different kind of transitions. So if samarium having different transitions, dysprosium having different transitions, lanthanide having different transitions. So that is the shows the what is the laser transition takes place in each and every lanthanide ions. So the technological interest in glasses containing lanthanide ions suddenly rise upon the development of solid state lasers. The incorporation of small amount of lanthanide ions in glasses is found to change the properties of the host material, and sometimes it could change drastically with the type of dopant and its concentration. This is very important. Whenever glass formers, if you see the borate glasses, B2O3 glass formers, you can add in the small amount, the incorporation of small amount of lanthanide ions in this glass. We are glass formers, we are adding less concentration only, up to 1 mole percentage or 2 mole percentage or 0.5% also. So we are adding less concentration of lanthanide ions in the glass host material. At that time, they found to be changing the properties of the host material, and sometimes it could change it drastically with the type of dopant and its concentration. So dopant means we are adding the lanthanide ions as a dopant. That lanthanide ions act as a active ion in the glass system. So by adding of the lanthanide ions in the glass material, glass host, it drastically changes the different kind of optical properties or luminous properties will be changes. So that is the mainly we are adding the lanthanide ions in the glasses. So this is the very important thing for the laser glass spectroscopy. Next, coming to the, so already in previous session also we discussed different kind of lanthanide ions. So again, so we are going to know about the what are the lanthanide doped glasses, that is coming from the starting from the lanthanum. So lanthanum to lanthanum, cerium, prismodium, neodymium, pramotium, samarium, europium, polonium, terbium, dysprosium, holmium. These are 14 elements of the lanthanide ions or rare earth ions involved in the laser class spectroscopy. So these are the different kind of lanthanide doped classes. Thus, it has been shown that the behavior of lanthanide 3 plus ions in glasses is similar to the lanthanide ions in inorganic crystal of low symmetry, except for the inhomogeneous broadening of the spectra due to the multiplicity of, so each and every rare earth ion having a different kind of multiplicity of lanthanide sites in glasses. It is because of this lower symmetry that forced electric dipole transition became possible, and absorption and fluorescence are observed in the lanthanide doped glasses. So whenever it will be act as a multiplicity of the lanthanide ions. At that time, the lower symmetry, the electrical dipole transition, became possible, and absorption and fluorescence are observed in lanthanide doped glasses. So that is the first point. The second one is the inhomogeneous nature of the lanthanide ions in a glass is beneficial for optical pumping with broadband sources such as xenon flash lamp, is because most of the spectrum is observed. That is why we are using for measurement of the absorption or measurements. We can use the luminescence measurements. We can use the xenon flash lamp because most of the spectrum is observed. By using the xenon flash lamp, we can observe the complete electromagnetic spectrum. We can observe in this using the xenon flash lamp. In addition, the effective cross-section of the amplified spontaneous emission, which limits the excited state population, is less. Both of these features combine to provide greater energy storage in the glass than in crystalline materials. Compared to the crystalline material, we can provide the greater energy storage in the glass materials, that is compared to crystalline materials. For energy extraction, however, the inhomogeneous spectroscopic properties can be determined because of the optical spectra of lanthanum 3 plus ions in glasses are homogeneously broadened. Glass laser provide some tunability. So glass lasers provide some tunability. That is, tunability percentage will be less, equal or less than. Equal or less, tunability is less than or equal to 10%. Is not possible in crystalline host. Next, coming to the what is the important centric applications of the rare earth or lanthanide ions. So see here the conventional matter physics also we can use the different kind of rare earth ions. Next, atomic physics. Next, material science, communication, industrial applications. Next, imaging, medical science, biology, plasma physics, astrophysics, particle physics. These are all different. This is the lanthanide doped laser class spectroscopy is a vast subject. We can use different kind of applications of the different kind of lanthanide ions. So these are the different kind of applications whenever using the lanthanide or rare earth ions doped into the glass materials. So these are the different applications of the rare earth material applications. Next, coming to the variation with the bond nature. How structural nature or bond nature, how it really happens whenever glass material is host material is doped into the lanthanide ions. See here, this green color shows the lanthanide ions. Inside there are the oxides. So lanthanum ion 3 plus is oxide. This is a ligand atom. Blue color is a ligand atom. So each and every ligand is nothing but a negative charged particle surrounded by a positive cation. Okay, these are the very important. So these ligands takes place in the bond structures. So see the here in this graph, energy versus intensity. This mu is the frequency wavelength. So here this is the intensity. This is soft intensity. This is broad intensity. This is very broad. These are the emission peaks. We can say, for example, these are emission peaks. By using this emission peaks, we can calculate the stimulated emission cross section sigma. Stimulated emission cross section parameter is sigma equal formula equal lambda p4 equal 8 pi c n square delta lambda effective. That is effective wavelength. This is radiative transition property AR. This is. So by using this formula, we can calculate the stimulated emission cross section by using the variation of bond natures. See here the energy versus intensity. So this delta mu, this is the width of the band. This emission band, how much width is it? By using this one and this one, we can calculate how much energy wave bandwidth is how much. The branching ratio is nothing but the relative intensity area how much each and every emission peak. What is the relative intensity area? We can, by using the this area relative intensity area, we can calculate the branching ratio of the each and every emission peak. So here delta mu, that is the full width of maximum. By using this graph, we can calculate the full width of maximum also. That means each and every peak how much intensity, and half of the intensity peak, we can calculate the how much full width of maximum, delta mu. Branching ratio is the relative intensity area. These two parameters we can use to calculate the each and every emission peak. By using this data, we can calculate the stimulated emission cross section. Lambda p is the each and every emission peak wavelength, lambda, that is 4 times 8 pi c is the speed of light. N is the refractive index of the glass material. This effective wavelength is transition probability. These are, by using this relative transition probability, we can use to calculate the stimulated emission cross section. This is the variation with bond nature. Next, variation with ligand environment. So previously bond nature, next variation with ligand environment. Whenever ligands, previous case we can added only one ligand. See the different kind of ligands added to the lanthanide doped material, how emission peak will be there. So first you see this, only 3 types of ligands is added into the lanthanide ions. At that time you can take space only single sharp intense peak. If you added into 4 kind of ligands into the lanthanide doped material, we can see brown nature. If you add more number of ligands, it will be split, the each and every emission peak will be splitting event, that is stark splitting. So that is degeneracy will be takes place. At that time splitting will be takes place because of you are adding the number of ligands into the lanthanide doped material. Whenever adding the more number of ligands into the lanthanide doped reactive ion, at that time star splitting will be takes place. If you are getting only 3 types of ligands, if you add it into lanthanide ions, you can get sharp peaks. We add more 4 numbers, we can get broader end. If you add more than 4, it can split into the different kind of emission peaks. So this is called star splittings. So in order to improve the emission cross section and lifetimes, the addition of various formers and the various of chemical compositions are to be performed, which could change the asymmetry of lanthanide ions in the covalence between the lanthanide 3+ and ligands. So here ligand is the important role in this ligand environment. So that is the variation with ligand environment. So whenever adding the additional number of ligands into the lanthanide ions, it will be getting the emission will be splitting more numbers. This here see 1, 2, 3, 4 star splitting. That is mainly due to the because of adding of ligands into the lanthanide ions. So these are the variation with ligand environment. Next, these are the references which covered the topic. So first is the these are the something glass structure by spectroscopy of the glass material, the structure of by spectroscopy. This other one is a laser and excited state of rare earths. These are different textbooks and also some references cover the 2 topics. So next section will be continued. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.